Good afternoon, everybody. Welcome back from lunch and welcome to this second last session of this wonderful conference. First up, we've got Wolfgang Hayek from NeSI. He's going to talk to us about work he's done on LFR-IC code, which is related to the weather modeling that they're doing at NeSI. Thank you, Wolfgang.
Kia ora tatou ko Wolfgang toku inoa. I hope you can all hear me well, and I'd like to talk, about my two favorite topics, weather and climate codes and HPC today. Also, a big thank you goes out to the people that I've been working with across the Unified Model Partnership. They're quite a lot, so I didn't list them all here. All right. Quick overview. So at first, I'll talk very briefly about weather and climate forecasting at NeSI. So I've been talking about this several times over the years, so I will keep that very brief. And then I'll discuss the matters of HPC efficiency and performance portability in that context, and then come to some optimization work that I've done on the new Alfred code that will replace the unified model soon. Okay, so you might be aware that NeSI runs operational weather forecasting every day, and we have a multitude of climate forecasting projects. I've put a snapshot of one of our highest resolution models on the right-hand side, and it's the New Zealand convective scale model that includes New Zealand and some ocean around it, just as an example. We also have other models that we use for climate forecasting, but most of our work is based on the unified model, which is made at the UK Met Office. And climate models always feature as one of the HPC grand challenges, but for weather forecasting is a challenge in that as well for computation. So computational efficiency for these kind of things is paramount, not just because of cost and the ability to run at high skill and fidelity, but also, of course, to make sure that we don't have a huge resource footprint. So, I mean, you wouldn't want to run climate models and then contribute to the problem yourself by producing lots of greenhouse gases just to run these models. Of course, one of the most recent developments for improving models and speeding up things has been machine learning. I won't talk much about that, but just as a quick aside, with machine learning, you can get to really incredible speed when it comes to the forecasting itself that runs via inference, but you still have to train your models, which can be very expensive, very resource consuming, and you still need the output from weather models to train machine learning models. So I'm not an expert in these things, but my understanding is that you cannot train at least long-term or longer forecasting models just from observations alone. There's a very good blog post about the subject if you're interested in it. That I've put here below on the ECMWF webpage, so well worth reading if you're interested in the subject. Okay, so of course, inevitably, what happens over the years is that these models get more and more computationally expensive. On the right-hand side, you see a timeline of the resolution of unified model-based global models. We don't run these ourselves at NeSI because they are extremely computationally expensive, but we need the global models as boundary conditions and initial conditions for our own models. And you can see here there's been an exponential growth in the spatial resolution, so the number of grid cells that make up the global atmosphere. And that's not the end of the story. So this is just spatial resolution. If you increase spatial resolutions in these kind of models, you also have to decrease the time step. That's inevitable. So you have to run more time steps, which adds to the amount of compute you have to do. And also people want to increase the complexity in the model. So they want to refine the physics descriptions, add more physics with higher fidelity, and all of it, of course, compounds the amount of computational work you have to do. Okay, so what does it mean for our HPC efficiency and HPC developments? Here are some figures from the IEA about the resource consumption of data centers. Of course, that's much bigger than just HPC alone. HPC is a niche in there. Data centers evidently do all sorts of things, but it's still quite interesting to look at the footprint of that. So it's estimated that globally in 2022, data centers used up about 1 to 1.3% of the entire global electricity consumption. And I suspect this is bound bound to rise further because obviously people want more compute, they want more services, more data storage, and so on. And in that way, data centers also have their own contribution to greenhouse gas emissions. So sitting at 0.6%, so it's not absolutely massive, but still it is a concern. So this is one side of the coin, that of course you try to be as energy efficient as possible. The other side is you couldn't even get to the performance levels that we expect without being energy efficient, because it simply would not be economical to build machines that have a huge amount of computational capability, but also a very high energy footprint. So this year saw the introduction of the first public exascale system, the so-called Frontier HPC in the US, and it runs at the total energy budget of a whopping almost 23 megawatt, and that's just for the compute alone. So that does not include cooling and auxiliary systems. A small HPC was built in Europe. It's called a pre-exascale system. It has about 1/3 of the computational capability of Frontier, comes in at 6 megawatts. And the crucial number here is on the right-hand side. Both of them have an efficiency of about 50 gigaflops per watt. And when you look at what happened over time, you can look at data from the Green 500 list. If you're not familiar with that, Green 500 is part of Top 500, which lists twice per year the 500 most capable HPC systems in the world. And then years ago, people came and reshuffled that list and reordered it by the efficiency, so the gigaflops per watt that you get, and called it the Green 500. So the top Green 500 system is not necessarily the biggest system, but the most efficient system. And so 10 years ago, if we had tried to build an exascale system out of the most efficient Green 500 machine, you would have landed at about 300 megawatt just for the compute. So, I mean, of course, you could have done that, but you would have had to put a power station just right next to it. I compared here to the energy output of Tucano hydropower station on Lake Taupo. And again, that's just for the compute, so not for the cooling. But over time, people were very crafty, and so they built machines that are way more energy efficient and way more capable. And so that's how Frontier ended up at the budget of just under 20 megawatt. And as you can see in the timeline here, that just happened last year, so it was really right on time. And these systems are either CPU or CPU plus GPU HPC. So Frontier is heavily GPU with a bit of CPU, but there are other systems that are smaller that run on CPU only. So which brings us to the next topic. So how did people actually make that happen to be so energy efficient? And so inventive as people are, there's been lots of developments in that field. So when you use a CPU, of course, you don't just use a plain CPU, but you have also some little tricks that the CPU does for you, which come with lots of acronyms like AVX for vector processing, or lately AMX for matrix operations. Then you have different caches. You have different types of memory. Intel introduced high bandwidth memory, which was long known for GPUs, but has now come to GPUs as well. Then you have XPUs and APUs, so which are hybrids between CPUs and GPUs, and so on. So we're basically looking at quite a large number of different options that you have to achieve this kind of energy efficiency and performance. So a term that's sometimes used in that context is the Cambrian explosion. Was previously used for AI related compute capabilities and AI models, but I think it's probably fair to say that we're also entering an explosion zone now with CPU and GPU compute for general purpose compute as well. And so the problem now is that, sure, we have efficient hardware, but we also want to use it with the software. Otherwise, you don't actually get this kind of efficiency and performance. And because no one wants to write software for every possible combination of things and every possible specialized hardware, we have to make sure that the software is not only portable, but also performance portable, so that you don't have to write specialized code, at least for the heavy lifting parts all the time. So that's the ideal. However, as much as you can try to write, or you can do that to some degree, write performance portable software, you will still not be able to avoid some degree of specialization. And one of these examples of that is CPU caches. As I'm sure you know, CPUs have large caches to make up for memory bandwidth constraints. And so you do have to utilize that to really get good performance, even if you write your code well and so forth. So you still have to worry about that as well. And so in the end, to really get good performance, you need to do both. So you need to write software that is performance portable, but you also need additional optimizations that can handle particular cases such as CPU caches. Okay, so that brings us to Alfric. So as I said initially, Alfric is a new weather and climate code that will replace the unified model in a few years' time. It's named after Lewis Fry Richardson, who was a weather forecasting pioneer in the last century. And Alfric is a completely new development. It uses a separation of concerns model to handle this kind of portability issues, where on the top level, you have the algorithms that make up the code or that formulate the physics. And these algorithms put together a bunch of kernels as building blocks, and these kernels do all the heavy lifting. So these are small code fragments that do particular operations, and there's a middle layer called the SI layer here in Alfric, which assembles these kernels into the algorithms. So you can look at that as a kind of a domain-specific language approach. And the beauty of that is that when you port Alfric from one platform to another, you don't have to change the entire code, but you can just focus on a bunch of kernels. And some of these kernels won't be even that important for performance, so you can probably focus on just 5-10 kernels or so to get the most performance out. And so if you have to specialize a kernel for a particular piece of software, a particular piece of hardware, you don't have to go through the entire code. You can just work on this particular kernel. And this is now where my contribution came into the code. As I said earlier, you cannot avoid some degree of specialization, and in this case, the wish was to exploit CPU caches better, so to make sure that the data that has been loaded into cache from the slower main memory is reused as often as possible. Before having to go back to main memory and fetch more data. And loop tiling, also known as loop blocking, is a very well-known technique. It's been around for probably 20 years or something like that at least. And it changes the order of computation. So instead of using a random order to compute cells, say here in this case of a cube sphere, this is the mesh that Alfric will use for global models that you see here in the top right. So instead of say a random order or a row by row or something like that, you compute cells tile by tile. And if you have data that is defined on the boundaries between two cells, you only have to go and fetch it once from main memory, and you'll be able to reuse it several times. Or the same with data that sits on vertices. You can reuse it several times, and so you make better use of your cache. This example here also uses coloring. This is a technique that enables thread-based parallelization. That is important here because if you don't separate out the cell computation with these colors, so colors means that you compute in parallel over tiles of the same color. Otherwise, you risk a problem called race condition, where threads can override each other's results. And so by separating out the tiles with colors, you keep them separate. And that gives you actually quite good performance improvement. So I tried this out with one of the Alfric kernels that was strongly memory bound. That means that the CPU was waiting most of its time for data to come in from memory. And if I tiling, you can see that here on the right, where I compare the tiled case versus the non-tiled cell-by-cell computation, and I get speedups of better than 25% in some cases with larger tiles. And I've calculated that for different numbers of threads that run in parallel, and you can see that it holds pretty well. Even with more threads, I still get pretty good speedups. It is quite a complex game, though, with this cache reuse. So there's many factors that go into it, like the particular CPU model that you have with particular cache size, then what kind of algorithms you use, how memory bandwidth bound is it? How optimized is the code, and so forth. So, it's difficult to make predictions, but it basically this loop tiling gives you one tool in the toolbox that you can use to speed up code. Implementing tiling in principle is relatively simple, but it wasn't in the case of Elfric because the code is pretty complex. There are several reasons for it. Part of it is the partitioning. You can see it here on the right, where you have boundary conditions called halos, and you need to you need these halos for data exchange. So I had to tile that separately. Then there are inner halos because people wanted to overlay communication of this boundary data with computation in the inside of a partition. So there's several constraints that you have to work with, and Elfric treats its meshes as unstructured. So I had to write algorithms that try to find out what kind of mesh I'm actually looking at and how do I tile that and so forth. So it's been quite a long journey, but in the end, after 1,000 lines of code, so to handle all these different cases and so forth, I got there. And that brings me to my summary. So basically, for weather and climate forecasting, but of course also for many other disciplines, machine learning especially, deep learning, energy consumption is an important consideration. And people have been very inventive with building efficient hardware, but you also need to make sure that your software can actually use that. It's easy in the case of machine learning because there are some friendly people that that port these things for you, but in case of weather and climate codes, it is much in your own hands to make that efficient on these kinds of platforms. And so ideally, we would want all software to be fully performance portable, so we don't have to change a thing, let all the work be done by the compilers and by the hardware itself. But in reality, you won't be able to completely get there. So you do have to have some hardware-specific optimizations that you need to be able to leverage. And in this case, I implemented a loop tiling scheme that you can turn on and turn off. So if you don't need it, or if it turns out that it's actually worse for performance, which can also happen, you can always turn it off. And that's the end. Thanks very much for listening.
Thank you, Wolfgang. That was a tremendously interesting talk that you gave. I'm quite impressed by the speed up that you got from using these larger tiles. 25%, it's not something to sniff about. It's also quite interesting, this whole field of data set design and that overlap of making sure that what you design is both functional and efficient. It's a good talk. So we've got one question. So the question is, thanks Wolfgang for the great talk. Do we have an idea of how far or close the Elfric is from max CPU performance?
Ooh, that's a pretty big question. So Elfric is still under development, and at the moment the focus has been the scientific implementation and a baseline performance. So people have not spent so much time on driving it to very high performance levels. Also, how much how close you get to peak performance on the chip depends on the section of code you're in. So some code will be running at very poor performance, but very briefly, so it doesn't really matter. Some code will be running actually quite close to peak performance. So my guess is, at least from what I've seen from the predecessor unified model, you can probably get to 20-30% peak flops on a CPU with these kind of things. I think with GPU, it's probably a bit harder to actually get to such high performance levels. So don't quote me on these numbers, but I think probably something like between 10 and 20%. So, but you might get into situations where you have a kernel that runs particularly well, and then you might actually get 80% for a brief amount of time. But over the average over the whole code, I would be surprised if you get above 10-20%. And that's not even taking MPI into account. For these kinds of codes, you spend a lot of time communicating boundary conditions between the different partitions, and typically you would use at least 25-30% of your time just with communication, and of course that drives down your peak flops because you don't do any useful compute while you're communicating.
Oh, excellent. We've got another question. interesting question is maybe it's possible to use cache oblivious algorithms, many divide and conquer algorithms are, to deal with the caching efficiency more automatically.
Oh, that's an interesting question. I've never thought about that. So I can't really comment on that too much because I'm not familiar with how these algorithms work. I mean, one of the issues that it might face, but again, I'm just speculating here, is that the code is written in Fortran, and so a lot of developments are not available in Fortran without having to implement it yourself. But it would be an interesting thing to look at. So yeah, thanks for bringing that up. I'll have a look at it.
Excellent. And then the final question is, you didn't include cooling in your efficiency numbers. So how much does cooling change this?
I don't know the exact numbers, and I tried to find out, and I looked around online a little bit, but it's quite hard to get these numbers, and I guess it's probably also a little bit of the dirty secret of many HPC centers, how much energy is spent. You can probably double the energy consumption, I think, if you take everything into account, so the cooling and all the auxiliary systems you need to run your HPC. It's probably something in that ballpark, but I have not been able to find out, so it would be interesting. I agree.
Excellent. Well, thanks again, Wolfgang. It's a great, interesting talk. Thank you very much. Next up, we've got Kevan Cote from EcoIndex. Now, Kevan's going to talk to us about repurposing GIS data and using neural networks to identify land use types. Kevan, over to you.
Thank you very much, Charles. Appreciate the introduction. Yeah, so I'm coming from the EcoIndex. I'm working as a data scientist with the main goal that we are trying to provide guidance towards restoring, protecting, and connecting native ecosystems to a percent of about 15% of the original land cover by the year 2121. So we're providing guidance. We're not doing the physical hard digging, unfortunately, in this aspect. But yeah. So first off, as you can imagine, here we have an ecosystem. This is a bit of native ecosystem across the Waikato. And if we picture this throughout the years, as it starts to grow, as it expands, I'm not sure if you got that little animation, but we're watching these as they go through the years. And what we want to do is measure how much they have grown. This provides a health indicator, sort of how well the ecosystem is doing, whether it's thriving, whether or not. So this is a very important indicator. And on this sort of scale, it's quite easy. We can do this by hand, but our goal is to do it across Aotearoa. So you can imagine this is the case where we really start getting into machine learning and automating detection, and that can really help us along. The first step for anyone who's built machine learning models is obviously training data. Usually it's photographs, but in our case, because we're using land cover types, different ecosystems, GIS data becomes very, very important. We're lucky that in New Zealand, we have the land cover database, which is a great information for different ecosystem types, spanning most of the country and in reasonable accuracy as well. I'm not going to say it's perfect, but reasonable accuracy. So our idea is let's use that data. It's out there. We don't have to re-go and find it. It's pretty much out there. We also have partners within different regional councils that have provided us GIS layers of their regions, which are a bit more up to date, slightly more accurate because it's on a smaller scale. And then we have industry partners as well that we're grabbing data from. So we've had this idea that we have all this data together. Let's use it for our purpose. On the other side of things, so that was our training data, if you will. Now we need the image that we actually need to detect. And through this program, we've partnered with Planet Satellite Imagery, who have provided their 4- and 8-band multispectral images for us. These are a 3 meter per pixel resolution, so fairly high resolution. And then we also have access to their SkySat, which is 40 centimeter on-ground resolution per pixel. So incredibly high resolution, but we haven't really dug into that yet. I'm just going to be talking about the 4-band in this case. So I've talked about, we have all this incoming data. We have this image in the green here. You can see I've just overlaid the indigenous forest layer on top of a part of the Waikato. How do we transform that into the neural networks, into the machine learning frameworks that we're used to? And that's essentially where this program sort of flourishes. So be patient here. I have 3 slides that I'm going through in detail. I'm sorry if I lose some of you, but I promise I will come to an example at the end just to keep your attention. So we've discussed these 2 sources of input data. We have the satellite images, and then we have these shape files. And what our framework does is it pulls from the GIS domain and it puts it into the machine learning domain that you'll sort of see. But the first thing we need to do is check if our 2 input sources actually match. So we go through and check the coordinate reference system. If they are different, we can convert one or the other. That's an optional step. And then we have an optional crop as well. If you've ever worked with satellite imagery, sometimes the tiles are a bit skewed. They're not nice square tiles. So you can crop it in just to make sure it's a nice square tile, easy to work with. We then grab those images, and from the satellite image, we turn it into a NumPy array. And that's sort of the first step that we're actually, taking the GIS, and that's the first real transition that we do into the machine learning realm. We then save that NumPy array locally for use later. Just as a little note there, we also grab the satellite and save it as a PNG, just depending on the type of neural network. Some of them are really easy with a NumPy array directly. Some would rather the PNG file, and etc. So we had kept that option open. We then go back and we grab that shape file. So we're going from a vector file and we need training data. So we need it into a PNG. So it's a bit of a 2-step process. We used all open source GDAL libraries, so they sort of do it in 2 steps. So anyway, we grab that shape vector file, convert it into a raster GeoTIFF, and then convert that GeoTIFF into a PNG. It's slightly convoluted, but what we end up is 3 sources of data. We have a NumPy array that originated from that satellite image. We have a PNG of that satellite image as well. And then we have another PNG of the shape file that's our mask. And you can probably start to recognize this is the perfect input data for a neural network and for many types of neural networks. So that's sort of the next step of what we did. And look, I'm not going to take credit for this. I grabbed this framework from GitHub. It's open source. He has a lot of very good other sources as well for different types of neural networks. So please check that out. But what we're doing is we're now grabbing those input data that we made in the last step. And then we're doing a process called patchifying. And really all that is you're taking an image and splitting it up into smaller images. It's just a way of handling large data a little bit easier. We then create a NumPy array of those shape files. So now we have both inputs as NumPy arrays, and then we're throwing it into a data generator. And that's the one step that sort of stands out from the standard example, because we're working with, in this case, an image of the entirety of the Waikato with 3 meter per pixel resolution. It's a fairly large image. And I ran this all locally on my GPUs, and it needed to be split up. So that data generator just trickles in the data during the training process a little bit at a time. We run it through a standard UNet, nothing special about that. I chose a UNet just because it was part of this example. But again, completely open to run whatever neural network suits the type of data the best. And then we save that model locally. Now, sort of the fun part about this, and I promise this is the last set of slides that we'll go through that look like this, then we get to the example. We then pull in a new satellite image. So now we're starting to predict on unknown imagery. Convert it to a NumPy array using that previous step. Again, we patchify it because it's much easier to run an inference on small images. And then on each patch, we do a prediction. We then grab all those separate patches, shove them back together as a single image. And then we go through that and find the contours, because what we've done is we're now doing that transition back to GIS data. We had it pulled apart in the neural network working with NumPy arrays, but now we need to transition back. So we go through pixel by pixel using the OpenCV library to find the contours. which in this case are blobs, and will work out to our predicted ecosystems. We write each of those contours as a polygon file, which is then very easy to convert back to a shapefile using some of the information from the original satellite image, like the coordinate system and the bounds, etc. So again, apologies, but let's look through a little example that I ran. What we did is we grabbed a photo of the Waikato, most of the Waikato, as you can see, and then I overlaid the land cover database on top of it, which you can kind of see in gray. It's a bit hard to see here, but this is indigenous forest on top of the Waikato, predicted from 2018, so a little bit out of date. Nonetheless, we ran it through, and it trained rather quickly, about 1.5 hours. With that input data, that was running through 100 epochs using 2 Titan V GPUs, 12 gigabytes each. So it's a desktop setup. It doesn't need to be done on a giant infrastructure, which is always beneficial. And then the actual inferencing of this image only took about 15 minutes to run. And all the pink that you can see is the predicted land cover, and it's overlaid on top of the gray, so you can see a few spots where it missed. But if I zoom in here, we can have a slightly better look. Now, this is just an example. This isn't meant to be our final product. I wanted to see how our framework was doing, so I use this. But nonetheless, it's done. It surprised me how well it did. Let's put it that way. I ran a quick intersection over union calculation at 67%. So, I mean, not the best, but not terrible either. What you see in red is the intersecting 2 points, and then in yellow is sort of the over and under prediction of each of the models. So room to improve, but gives me hope that we're going down the right path in any case. So currently, what I showed you was we're looking at indigenous forests. That was the land cover database layer that we pulled in. What we're actually looking for in our program is Kahikatea forest and wetlands specifically. Those are our 2 priority ecosystems that we're looking for. The reason behind that is they are the most depleted from the original land cover of New Zealand. So they have the most of our attention right now. What we're doing is pulling in more time points. First off, Planet Data has an image of the entirety of New Zealand about every month, and going back about 10 years. So we'll have approximately 120 time points of New Zealand that we'll be able to train on and sort of get that temporal aspect of how the ecosystems, one, change throughout the seasons, because that's very important, especially for wetlands as they grow and shrink. And then, of course, how they're expanding as they're planted and rehabilitated. I didn't mention this specifically, but that input NumPy array, that was the initial sort of part of our framework, has 4 bands right now. So that's the 4-band Planet Data, which is red, blue, and green color, and then a near infrared layer. What we're doing is adding to that NumPy array. So we want to put synthetic aperture radar as one of the layers. That'll give us a soil moisture estimate. And then a 6th layer will be LiDAR to have an elevation profile as well. And these all work together to go into that neural network and provide more data for our predictions. So that's what's happening right now. And hopefully in the next couple months, we'll have that implemented. A few future steps. So as a bit of background, the EcoIndex program runs until June 2024. So next year in June, but we have plans to keep going past that. So beyond that date, what we'd really like to do is start to pull in open source satellite imagery. We understand not everybody has the ability to work with planet imagery, especially on the scale that we are. So being able to use open source, even though it's quite lower resolution, Sentinel is about 10 meters per pixel versus 3, but it can still be quite beneficial, especially for larger classification problems. I want the ability to be able to easily swap between neural networks. Anyone who's sort of worked, I mean, you know, it's fairly easy. We're bringing in NumPy arrays. Those are ready to really slap into anything. If it's a mask RCNN, whatever sort of neural network you might want to work with. It's not that hard, but it would be nice to have a few of the more common neural networks ready to go for people to experiment easily without having to do too much coding in the back end. And then we also want to identify further ecosystem types as well. Currently, like I said, kahikatea and wetlands are 2 priorities. But in an initial analysis, we actually went through most of the ecosystem types and what is remaining from their original extent, sort of pre-human existence. What this graph sort of shows is that in the low-lying areas on the right-hand side of the screen, they're the most depleted. So that's where your kahikatea are, your swamps, your fens, mostly because these were prime farming areas. So a lot of them have been cleared for agricultural use. So they require attention where people are hoping to bring these back. But nonetheless, as we start to get those worked out, we'll be working our way left on that map and bringing in some of those ecosystem types as well. And then I want to sort of throw this out because we've focused on ecosystem types here, but if you look at this holistically, our input data is shape files. That doesn't have to be ecosystem types. It could be city planning. It could be finding houses. It could be, it's anything that that we want it to be. So I'm really curious to sort of know what would other people want to use this sort of predictor for. What sort of data is out there, and that's what we're hoping to do, is reuse and find new uses for this framework to help others. Namahi nui, and thank you all very much.
Oh, thank you very much, Kevan, for that very interesting talk. So I've got a couple of questions popping up here. So first of all, how are you planning to use the extra time points as just more data, or will you train or predict on time series of images as well?
Yeah, currently it's just using it as more data. We don't have part of our neural network actually looking at that that growing extent just yet. But that is the next step as well, is to say, actually recognize those growing ecosystems to be able to pick up on which areas are doing better, especially ones that have involvement from people investing money and time into them. It's a sort of a measure that we don't really have available to us right now.
Oh, excellent. Next up, so do you make use of workflow engines in your pipeline, or each one of these steps run manually?
I love the idea of workflow engines, but I haven't implemented it that far. That said, they're not separate steps. So we work a lot with Docker containers and Dockerizing sort of each step along the process. They're also done in Jupyter notebooks, which you can argue, yes, that is step by step, but at least they're laid out in front of you, and they're all functionized as well. So if people want to just import the helper functions into a workflow that they already have, then that kind of takes care of the ugly looking back end, if you will, makes that step a little bit easier. I did also forget to mention that this is all open source work. So June 2024, this will all be released open publicly for other people to adapt.
Good, excellent. Next up, I've got a question on if you can please comment on the use of SIR for soil moisture. The question is, how accurate is that?
Yeah, so it's a bit of a debate. As part of the Eco Index, we're actually partnered with the Geospatial Research Institute down in University of Canterbury, and they have a program called Rongawai, which has been using Air New Zealand planes to run up and down the country and get very accurate soil moisture readings. So we will be incorporating that, those sort of measurements into our models, but that data is not quite ready yet. The idea of using the synthetic aperture radar is, one, there's a lot of commercial sources for SAR data, especially in fairly high resolution if you're willing to pay for it. Sentinel-1 has open source SAR data, and it's global coverage. So that makes it a little bit more adaptable. As far as the accuracy of soil moisture, it's more of a relative measure. The SAR measures essentially the scatter reflection of the radar itself, which loosely translates into soil moistures, but it can get a bit confused around treetops, et cetera, because you can't actually penetrate through with most available bands easily. all of this kind of going around to say it's our way of balancing that easily available data right now for us, and then specifically aiming it towards wetland detection. Most of the ones we're looking at are sort of the lesser vegetated wetlands. So hopefully that'll help us sort of differentiate between vegetated non-wetland areas and the wetland areas more clearly than the 4-band planet imagery.
Excellent. Thanks. There's a couple of more questions which I'm gonna ask the people who asked the question to get in touch with you specifically after the talk. So I'll catch up with you. Thank you again, Kevan.
Perfect. Thank you.
Great talk. Next up, we've got Josh and Maxime from Matai, NeSI, and NeSI, and they're going to talk to us about fMRI workflow and the lessons they've learned on integration and reproducibility.
Kia ora tātou. I'm Josh, and I'm presenting today with the wonderful Maxime from NeSI and NeSI. You probably heard my colleague Aaron speak yesterday and chair a session, I believe, earlier today as well. So to provide some background here, Aaron provided a great overview of who we are at Matai, but just really quickly, we're a medical research institute, and at the center of all of our research is cutting-edge, world-class MRI imaging. And one form of imaging that I'm particularly interested in is called functional MRI or fMRI. And basically what this does is it allows us to measure blood flow as a proxy of brain activity, and then to correlate time series patterns in blood flow throughout regions of the brain to create networks that then, by understanding those networks, we can understand behavior and disease in different individuals. We wanted to build a workflow with the help of Maxime and NeSI because in our ongoing project, we've already got over 200 scans acquired from young rugby players and athletes. And this is to help us better understand concussion using functional MRI. Imaging data sets are large. For each session per subject, it's over 1 gigabyte of data. And even running on 8 cores, this is going to take 6 to 10 hours of computation per session before we can even think about doing group analysis. Throughout this talk, you're going to hear Maxime and I refer to something called BIDS format a lot, so I thought I'd touch on it quickly. This stands for the Brain Imaging Data Structure, which is effectively one format to rule them all, created by the neuroimaging community. And this is basically made to be able to share data more easily for 2 main purposes. The first one is collecting MRI data is expensive and hard. So being able to openly share it and allow people to answer their questions quicker is a main motivation. And then the other one is in the neuroimaging field, there's been issues with reproducibility in the past. So by adopting the BIDS format, it makes it easy to share data sets so others can verify analyses that have been published in the literature. As I mentioned, BIDS is community driven. And because of that, it's compatible with a lot of the open source community driven tools we're going to cover that we built into the workflow. Just to provide some scope about what we actually had to build into this workflow, the first thing is formatting our images. So when these pictures come off of an MRI machine, they're actually in 2D arrays. And to do fMRI analysis, you need at least an anatomical image and a functional image. But we need to convert these from arrays of what we call DICOM images into 3D or 4D nifty volumes. And there's just a 4th dimension for the functional MRI images because we've got time in addition to our 3 planes of orientation. Once we've done our DICOM to nifty conversion, we need to make sure everything is compatible with the BIDS formatting. After that, we actually want to take a look at our images and decide, is it even worth running the analysis on? And so there's a lot of ways to assess the quality of a brain image. So I've just provided a very simple example for the sake of this presentation. But on the left, for whatever reason, when the images came off the scanner, about the top third of the brain was chopped off. So this is going to fail. None of our software is going to run on this properly because it has an expectation of what it thinks a brain should look like. So we're just going to reject that from the beginning. Whereas the image on the right, it's a bit blurry, but that'll be perfectly fine to run our analysis on. Once we've determined image quality, now this is where the heavy lifting takes place in the form of pre-processing. I could spend an hour probably just on this figure here, but for the sake of keeping it brief, for each session, for each subject, we need to take their anatomical image and we need to register and normalize it to a template. Then we need to actually segment out the different tissues that exist in the brain. For functional MRI analysis, we're specifically interested in what's called gray matter. And then once those steps are done, we need to actually co-register our functional MRI image for that session back to the normalized image that we did earlier. So this is what can take 6+ hours of computation just to run this workflow here. Once all that's done, now we're going to do something that's called first level analysis. Basically what this step does is we want to generate statistical maps on a per session, per subject basis that then we can pass up to a group level analysis or machine learning to actually go answer our research questions of interest. We can do a first level analysis in dozens of ways. So in our workflow, we've made a generalized script in Python that will accomplish probably what most researchers want to do, or at least gives them a template that if they want to adjust it based on their research question, it gives them a huge head start. So those are the steps that we wanted to build into this. And luckily, we've got open source tools to the rescue to actually implement each step. So for image formatting, we use a program called HoodyConf. For image quality control, something called MRI QC. Image processing, fMRI prep and FreeSurfer. And then lastly, for the first level analysis, a community developed Python package called NiLearn, which is very flexible, as I've mentioned. So all these tools exist. The challenge is that nobody has actually taken the time to stitch them together. It's very common practice in the neuroimaging world for people to still just be running batch scripts on their machine for hours, days, or weeks just to try and get their analysis. So our motivation with this was to create a workflow that used SnakeMake to be able to run steps in parallel as much as possible to maximize efficiency, to recompute only what's needed if we found an error in the data instead of running everything from scratch all over again, to be portable so that if I've got a student who I just need to give 1 or 2 subjects to so that they can start to learn how the process works, they can do it on their machine. Or if we're trying to run large volumes of data, as I described earlier, we can easily scale up to an HPC like NeSI for that purpose. And then lastly, the aim of this is to be able to share it, to help other researchers get over the huge hump of just trying to get to this stage by implementing easily reproducible software stacks in Conda environments and containers. And I think with that, I'm going to hand over to Maxime, who's going to talk through the lessons we learned and the good and the bad and the ugly of implementing this process.
Thank you, Josh. So I'll start with the first step we described earlier, so the quality control, which involves using this HoodyConf tool to convert from the diagrams to bits, followed by the MRI QC to do the quality control. And as Josh said, we want to process data at the session level, so a subject can have multiple sessions, and we want to maximize parallelism, especially if we want to run on a massively parallel platform. The good news is HoodyConf can process a subject session independently, but in order to give us a data set which is bits compatible, it will also create some template files, and it will do them at the subject or at the data set level, which means that when you have the 2 tasks running in parallel that you see on the right, they may encounter a race condition when they try to write this template file. Next slide, please. The good news is the people who implemented HoodyConf, they were smart and they thought like, okay, maybe we should split these steps. They did, and it means for us as workflow implementers, we can actually run in parallel the conversion, and only after have these bits template files being generated, once it's safe to do, and only once. And once we have done that, the bits dataset is ready, and we can feed that into the MRI QC, and yay, that works. And at the end, we have a QC file, which is a CSV file where we collect the information, and that's where the scientists will actually tick off or on which dataset they want to process. Next slide, please. The next big step, the fMRI pre-processing. So for that one, we read the QC file I mentioned just before, and we feed this into the wonderful fMRI prep software, and which subsequently feeds data into the first level analysis scripts. Now, fMRI prep itself is a kind of a mini workflow, if you want, and under the hood, it binds together multiple tools, but one in particular we mentioned was FreeSurfer, so for the surface reconstructions. And interestingly, there are different resource needs for FreeSurfer versus the rest of the steps done by fMRI prep. So FreeSurfer will take about 9 hours, 3 GB of RAM per volume, whereas the rest of fMRI prep, it happened to us that sometimes we needed to crank up the RAM usage up to 25 gig, but only for 2 hours. So maybe actually we'd like to split these two steps so we use the right resources, compute resources for each step. And also there was some sad news is when we first tried to run it, FreeSurfer crashed in a very weird ways that we have not yet resolved, and we were not the only one having this issue. And the final thing is fMRI prep actually only process data at the subject level. So you can't really go down to the session of a subject level. And this is something we wanted to address to, again, maximize parallelism. Next slide, please. How do we tackle that? So we opened the box. So again, very good, very nice thing from the fMRI prep people is they allow you to run on your own the FreeSurfer and feed that after to the fMRI prep. And that's exactly what we did. So we can have FreeSurfer running in parallel. And that way we can separate the resource requirements for the two steps. And to allow for subject and session parallelism, actually, we had to do a little bit of an ugly trick, which is only for fMRI prep. Same story as with UDConf before. There are some files that can cause race conditions, so we injected a kind of a fake dependency. So for a given subject, you only run one fMRI prep task at a time. Next slide, please. This is a bit of a small crop of the big workflow, just to give an idea of what I just described. So if you look at the very top, you'll see FreeSurfer cross-sectional task, and this one are these 9 hours tasks that can run fully in parallel. They're followed by a little renaming of the files just to make it pleasant for fMRI prep to process. And then you have this kind of a fake dependency between the two fMRI tasks, which cannot run concurrently, but only one after another, one session after another. And then we have the first level analysis, which is done fully in parallel after the fMRI prep step. Next slide, please. Another lesson learned and a very good thing that has been provided by SnakeMake is how do you configure your workflow? And here there's two things that people want to configure. There's the things that when people want to process their own data set, they have some constraints which are specific to their project, and we want to have them in a project-specific configuration. In our case, it's in a configuration, a YAML file. For example, think about where is my input data, my output data, my license files, or maybe the size of my data set, which change a bit the resources I need. But then you have another set. Next slide, please. There is another set of configuration, which are the platform-specific one. And this one, maybe the users are a little bit less interested in fiddling with them. And that's typically how you tell SnakeMake to run on a workstation or in an HPC or in a cloud platform. And this is nice to have this division of configuration because you can prepare this what's called the profile in SnakeMake, and just give them to the users like, okay, now it's ready to go. Just take this one, you can run on NeSI, take this one, you can run on your workstation, and they only have to focus their attention on the other configuration. Next slide, please. Okay, a little summary of what has been described, and what was good in this experience was having a common format, the bits formats. It's very helpful as a workflow developer. We only have to follow the rules, sort of, and if the software follow the conventions, they can bind themselves together quite nicely. The other thing which was very good is a lot of this software was distributed as containers, which make it so easy to actually pull them and run them in a reproducible way. And the last thing was a combination of features. So having this SnakeMake profile, the containers and conda environments means we could easily reproduce the software stack on different platforms. Next slide, please. Okay, the less good or the bad, the granularity of the tools. So as I was trying to explain before, if your tool is only giving you access to processing the subjects, one subject at a time, means you can't do parallelism at the session. And for a computational good computational resource usage, you may actually want to do that, which leads to the ugly, which is how do you bypass this? And it depends on how the tool gives you access to sort of accessing individual steps. Next slide, please. And this gives me to this slide, which is for tool writers. If you want to be nice to your fellow workflow writers, please try to give an option on your software to output standard data formats. Actually, something which is even more important, in my opinion, give the flexibility to select where the files and the folders, the input and the output one, will be given, because if you constrain that, sometimes you don't know in which environment, compute environment, it will be executed. It can make workflow writer lives hard. If you can provide the software stack definition, that's very nice. If it's even packaged as Python conda, whoa, that's even more wonderful. If it's a container published on Docker Hub, this is a marvel. But the last one, which maybe is not the most obvious one when people assemble a software, is if you have something which has multiple steps in parallel steps, for example, versus serial sections, please make sure that even if you bundle it together, so it make it easy for one type of your users, some people may want to actually access these individual steps separately, again, for this reason of running things in parallel or avoiding race conditions when you want to output some summary figures. Next slide, please. So just a quick note about the work has been realized with, done with the consultancy service at NeSI. I won't say more about this because I think it already has been presented previously. But if you're curious about what we're doing and how we can help you, flick us an email at support@nesi.org.nz. Last slide, please. And on this note, thank you, everyone. Tēnā koutou, tēnā koutou, tēnā koutou katoa.
Well, thank you very much for that interesting presentation, Josh and Maxime. It's good to see that you managed to wrangle your fMRI pipeline using SnakeMake. So just a question from me. Did you guys also explore, when you started this project, using Nextflow, or did you just kick it off with SnakeMake and you're living with that decision?
I think we could say at the moment we're living with this decision. So yeah.
Having said that, I'm also a big fan of SnakeMake, so it's working quite well.
Also, I mean, okay, we have other people at NeSI experts more in Nextflow, but SnakeMake was also a good match in terms of here we are processing, as Erin mentioned in a previous talk with Alex, we are really processing a set of files from start to end, and everything is a dependency between files. So which means it's very well suited for a file-oriented workflow, which is SnakeMake.
Exactly. Yeah, good. Thank you very much. We don't have any other questions, so there's one that popped in just now. Just give me a second. So great talk. To what extent was the workflow customized for NeSI, or is it a workflow that you envisioned other institutes might also be running?
Yeah, so the intention was to help ourselves out, but to be able to distribute within NeSI, but then to share with collaborators as well, whether within or without New Zealand. Some of the last testing we have to do is just making sure it works on data from multiple scanner types, because site to site, sometimes we have a GE, someone else might have a Siemens or whatever. It should be robust to that because the tools we've used are compatible with those different types of scanners, but it's just a final testing. So an example is I'm about to share it with some colleagues down at University of Otago so that they can speed up their analysis with one of their PhD students they have down there.
Oh, good. Next question. Could the race condition issue be avoided by adding an initial step that creates symlinks to the input files in multiple different directories and then run the conflicting analysis from those different directories?
That's a very good suggestion. We have not tried it. And I even know, I didn't mention that on the slide, but SnakeMake has a lot of functionalities and we have not yet explored all of them. And there is one which is called shadow rules. And I think this is something where basically you sort of automatically create symlinks for your set of files, run the analysis within this sort of shadow folders, and only gather the final outputs that you want and copy them back into your file folder. So I think there's a way to automate that, but at the moment it's only on the to-do list.
Excellent. Well, good luck, guys. Thank you very much for your presentation, and thanks to all of our speakers in this session. So we can now move over to the final session, session 6. Thank you again.